Have you noticed the recent photo circulating online of the J-50 releasing fuel mid-air? That silver fighter trailing a fading trail of fuel mist across the blue sky, a seemingly simple maneuver that ripples through the calm like a pebble dropped into a lake. Is this merely routine testing, or a pivotal turning point in China's sixth-generation fighter development? Upon closer examination, the technical intricacies and strategic implications revealed by this scene prove far more profound than meets the eye. It may quietly herald the dawn of another leap forward for China's aviation industry. As a video blogger who has long followed military technology developments, my adrenaline surges every time I witness such test footage. Fighter jet trials, especially for cutting-edge projects like the J-50, reveal each publicly disclosed action as a piece of the puzzle, gradually sketching the full picture. This aerial fuel dump test is neither accidental nor routine. It represents a highly symbolic milestone in Shenyang Aircraft Corporation's advancement of the Northern Sixth-Generation project. It clearly signals that this sixth-generation fighter, which military enthusiasts hold in high esteem, has completed fundamental aerodynamic layout and power system validation. It has now formally entered the deep waters of system integration and extreme condition verification. This signifies that engineers are now assembling each subsystem, flight controls, fuel systems, avionics, and weaponry, like the gears of a precision clock, testing their coordinated performance under extreme conditions. Aerial fuel jettison stands as one of the core tests in this phase, its importance rivaling that of the first supersonic flight or weapon deployment trials. Why is fuel jettisoning so critical? Let's start with the most fundamental safety logic. For any jet aircraft, be it a commercial airliner or military fighter, a full fuel load can become a lethal burden if an emergency requires an immediate landing after takeoff. Aircraft landing gear and airframe structures have strict safe landing weight limits. Landing overweight could subject the aircraft to immense impact forces, potentially causing landing gear failure, structural deformation, or even disintegration. Thus, the emergency fuel jettison system becomes a lifeline for reducing weight in flight. It allows the aircraft to rapidly shed excess fuel, lowering total weight below the safety threshold, and thereby increasing the probability of survival during an emergency landing. For a heavy sixth-generation fighter like the J-50, with internal fuel capacity potentially exceeding 10 tons, the absence of reliable jettison capability could turn a single emergency return flight into a catastrophe. Thus, this test primarily validated the fuel system's reliability under emergency conditions. Can the lines clear obstructions rapidly? Do valves precisely regulate flow? Can pumps and seals operate stably under high pressure and velocity? These seemingly mundane components actually safeguard pilots' lives and protect billions invested in R&D. But the J-50's fuel dumping test extends far beyond safety considerations. Its deeper significance lies in serving as a comprehensive assessment of the aircraft's overall system integration. Modern fighters, especially sixth-generation models, are no longer simple mechanical assemblies but highly intelligent flying computers. When fuel sprays from specific nozzles on the wings or fuselage, an entire system is working in concert. The flight control computer calculates the optimal dump rate and timing based on real-time flight conditions, including speed, altitude, and attitude, to prevent fuel vapors from entering the engine and causing surge or fire. The fuel management computer monitors fuel levels in each tank and adjusts the center of gravity through distributed fuel lines as the dumping process alters the aircraft's mass distribution, thereby affecting its handling and stability characteristics. Simultaneously, the aircraft's distributed atmospheric data system and various sensors act like nerve endings, collecting data on airflow disturbances and pressure changes during fuel dumping, which is fed back to the flight control system for real-time corrections. All these measures ensure the aircraft remains stable and controllable throughout the weight reduction process, even optimizing its maneuverability. Looking back at the history of global aviation, fuel dumping tests have always been an essential step for new aircraft to obtain airworthiness certificates or military certification. In the civil aviation sector, from the Boeing 787 to the Airbus A350, all have undergone rigorous emergency fuel dumping validation. In the military domain, the US F-22 and F-35, as well as Russia's Su-57, are no exception. The J-50's uniqueness lies in its status as a sixth-generation fighter, whose system complexity far surpasses its predecessors. The integration of cutting-edge technologies means its fuel system is no longer a simple storage supply unit, but may become part of an energy management network. The J-50's testing progress appears significantly faster than external expectations. Based on publicly available information, the time span from the removal of the prototype's test pitot tube to the current specialized fuel dumping verification is only about 1 year. Comparing this to the J-20's development timeline, similar stages typically required 2 to 3 years. This acceleration is no coincidence, it reflects the accumulated strength of China's aviation industry over decades. As a cornerstone of China's fighter development, Shenyang Aircraft Corporation has amassed extensive expertise in heavy aircraft and stealth technology through projects ranging from the J-11 series to the J-15 carrier-based fighter and the stealth-capable J-31. Meanwhile, the Chengdu Institute of Aircraft Design's successful mass production and deployment of the J-20 have established comprehensive R&D workflows, supply chains, and flight test protocols for sixth-generation aircraft. This means the J-50 project can stand on the shoulders of giants, avoiding many detours. Simultaneously, the widespread adoption of new technologies like digital engineering, virtual flight testing, and AI-assisted design has significantly compressed the development cycle. Beyond fuel dumping, the J-50's specialized performance verification phase will inevitably include other high-risk, high-difficulty maneuvers. For instance, engine shutdown and restart tests in flight, simulating power loss during extreme maneuvers or combat damage, followed by restart and recovery, are critical for the variable cycle engines or next-generation high-thrust-to-weight engines, potentially fitted to the J-50. Another example is stall, spin recovery testing, where the aircraft is deliberately induced into a stall state to validate the flight control system's automatic recovery capabilities and the pilot's manual intervention procedures. These tests tolerate no margin for error, with each flight carrying immense risk. Yet it is precisely this dance on the edge of the knife that forges a fighter's reliability and combat capability. Online intelligence suggests the J-50 may adopt more radical aerodynamic configurations, such as tailless or blended wing body designs, necessitating significantly more complex flight control laws. These specialized tests are precisely for honing its muscle memory. Does this accelerated progress mean the J-50's timeline will be brought forward? Initially, based on the technological leap required for a sixth-generation fighter, observers widely speculated the J-50 might not enter service until around 2030. But now, this estimate appears overly conservative. If the fuel dump test signals the full-scale launch of specialized validation, the coming years will see intensive weapon integration, electronic warfare testing, and extreme environment flight trials. Drawing parallels with the J-20, which took approximately 4 to 5 years from a similar stage to final certification and mass production, the J-50 could reasonably shorten this cycle to around 3 years, leveraging its more mature foundation and efficient management. Consequently, the projections by some seasoned domestic military enthusiasts and analysts suggesting trial deployment by 2028 or delivery around 2027 are not entirely unfounded. Particularly given the international landscape and strategic imperatives, the Chinese Air Force's desire for a sixth-generation fighter is urgent. The U.S. Air Force's next-generation air superiority platform has entered the engineering phase, with service entry anticipated before 2030. Europe and Russia also have their own sixth-generation programs. An earlier debut for the J-50 would ensure China maintains a leading position or even takes the lead in the imminent era of sixth-generation fighters. Of course, optimism must be tempered with rationality. The final certification of an entirely new generation fighter depends on numerous variables: the full maturity of engines, the durability of stealth materials, the stability of artificial intelligence systems, and more. Nevertheless, the development pace demonstrated by the J-50's fuel dump test clearly signals one thing: China's aviation industry is advancing toward the pinnacle of aerospace technology with astonishing speed and confidence.